So the question is, why do we come all the way up here to sample these boulders that were deposited by a glacier some time ago? This is really a paradise for anybody who's interested in these environments. First day in Peru. We just arrived. Bit of a long journey, couple of hours from Lima to Coca Chacra, where we're going to spend a few nights to get acclimatized with elevation. The sun has just come out at 6:30 in the morning, and it's our second day in Peru. We're trying to get acclimatized. We're at about 1,500 meters above sea level, but we're going to climb to 2,500 today if we can. Okay, so third day in Peru. Yesterday we went for a walk here in the area. Today we're going to try to reach higher elevation, maybe 2,000, maybe 3,000 meters above sea level. Let's see how we cope with that. We'll come back here to sleep tonight, and then tomorrow we actually move at higher elevation. Day 4, we just arrived in San Matteo at 3,200 meters above sea level. So we were a bit worried about the climb today because it's more than 1,500 meters, but so far so good, no headache, and we feel alright. We went for a walk. You can see San Matteo down there, where our hotel is. We climbed maybe, I don't know, 100, 150 meters, maybe 200 meters in elevation. As you can probably hear from my breathing, it wasn't that simple at this altitude, but we are okay. The landscape is beautiful. We reached the white Christ. It's a big, giant Christ that can be seen from all over the valley. And tomorrow we're gonna go by car to La Oroya, which is for 3,700 meters above sea level. San Matteo down here is 3,200 meters above sea level. A very quick video today from La Oroya. Tomorrow we're heading to Tanta, our final destination, and from there we'll go up to the sampling sites. We're still along the main road that connects Lima to the Amazon basin. You see a lot of traffic behind me. La Oroya is a town that stretches along this very long road, and it is at 3,700 meters above sea level. So we're getting pretty high, and in fact today we reached 4,800 meters above sea level. Quite impressive. A little bit of headache, but we're still all doing fine. No major issues. Our friends have joined us yesterday from Spain and Peru, and we're all excited about the field trip that is coming. We passed by a lot of mines. That was a little bit sad to see the amount of pollution that they generate. I think mines is one of the main resources for Peru. Okay, so we are on our way to Tanta. Beautiful valley, amazing geology, amazing glaciology, crazy high mountains, beautiful glaciers, and we are probably an hour away from Tanta. We are at about 4,000 and maybe 500 meters above sea level right now. We are climbing our first moraine, this massive glacial deposits, which we're going to sample today. And it's not a big climb, but at this elevation, as you can hear from my voice, is a struggle. Amazing geology across the lake, and also more moraines everywhere around us. This is really a paradise for a glaciogeomorphologist or glaciologist, or anybody who's interested in these environments. Plenty of boulders to sample, which will tell us how old this moraine was deposited. And here is our valley. So in the next few days we'll sample a number of glacial deposits along this valley. This one that I'm standing on is the largest one. You see it has a very big left moraine and right moraine that joins towards the end. And you see this alignment of massive blocks. This is again a deposit by a glacier. So how do we know that these are glacier? Well, think about it for a second. They have a shape, a distinct shape. It's a line. They've been deposited by something. And what other phenomena could possibly carry something this size and be able to deposit it in such a perfectly geometric way? There are, of course, other, slightly more complicated evidence of this, but when you see the size of this boulders, there's no question that a glacier deposited this probably 40,000 years ago, something like that. But that's what we are here to try to understand, exactly how long they were deposited. Quick update is 7:30 in the morning. It's a beautiful day so far, but the forecast suggests that there will be a pretty bad storm later in the day, with lightning and snowing tomorrow. So our original plan was to actually go camping tonight up high at 4,700 meters above sea level, but we decided to be careful and safe and to actually change the plan. It's a pity from a scientific point of view, but we'll make what we can today. For as long as the weather is good, we'll go to visit some other moraines and sample more boulders, but we will not head to the valley head. I think it was the right decision, because up at this elevation, struggling with altitude, just lifting the rucksack, for example, it's tiring, and climbing a few steps is really tiring. Going into a very long walk up to the valley head, and then risking finding ourselves in a big storm and snowstorm, and it's really not safe. So safety is of primary importance when we do field work up in the mountains, and so I think we've done the right choice, and I'm sure there will be plenty of science coming from the many samples that we already collected and the many more that we will collect across the next few days. Okay, so we are at Lake Huantai, Laguna Huantai. It's a beautiful lake at 4,700 meters above sea level, and we're going to sample potentially the most challenging moraine for us, the most challenging deposit, because it's very young. It's what we call a little ice age deposit, so it was deposited probably just a few hundred years ago, but that's why we're here. We want to find out exactly when it was deposited, when this glacier was much larger than it is now and was covering the entire lake and was building this natural dam, which is the moraine at present. So the question is, why do we come all the way up here to sample these boulders that were deposited by a glacier some time ago? Well, the thing is that the surface of the Earth is constantly receiving cosmic rays which alter the isotope composition in the crystals of, for example, quartz. And by collecting these samples, we can then analyze them in a laboratory and identify the isotope content, and from there we can tell how old these samples have been exposed to the surface of the Earth. So in other words, how old a glacial deposit, a moraine, is. And that's crucial because it tells us that it gives us a time, and a roughly exact time, of when a glacier was actually here. From that, we can try to reconstruct the glacier and try to see what kind of climate was there at that time. So for example, if the glacier was here I don't know, 2,000 years ago. Then by reconstructing the glacier and analyzing some glacial parameter, we can tell essentially how the climate was 2,000 years ago. So we have a much longer perspective about climate change, which help us understanding what's going on in the present and also help us improving our prediction of the future of climate change and its impact on the cryosphere, on the glacier, on the ice and on snow. Hopefully you can see the big glacier up there. It's a classic tropical glacier because we are at that kind of latitudes, and what we're sampling today is this moraine, this glacial deposit in front of me, where there are a number of boulders, and those will be the ones that we will be collecting about half a kilo of rock to be sent to Australia in order to extract the exposure age of these rocks, and therefore the time when that big glacier was much bigger and was coming all the way to this valley and deposited this beautiful lateral frontal moraine. Today we are back to Pariacaca and try to sample the oldest moraine that we were able to identify. We have identified a number of good boulders, and we're now moving on to sample this. We hope that this could be as old as maybe the glaciation previous to the last one, so maybe 125 to 100,000 years ago. In a situation like this, it's interesting to see that not only we have the morphology that helps us understanding that this was deposited, this ridge here on the side was deposited by glacier, but we also have what we call the lithology, the rock type. All around us we have outcropping of limestone on both sides of the valley, but on this ridge we find granite, which is a completely different type of rock. We find conglomerate, and none of these is available from the side of the valley, which means these have been transported a long way. Now their size, their relatively lack of roundness, it's a clear indication that no other agent but a glacier must have been able to transport these big boulders and deposit them over here. So we have the morphology telling us that this was a moraine, a glacier deposit, but we also have the lithology, the rock type. So we just finished sample this boulder to the left, which we think and hope will be very old because we are on the shoulder of a glacial valley, so we think it could be last glacial maximum, so called. And Brice and Lucy are actually doing a measurement of what we call the topographic shielding. In other words, because the age that we measure on the samples is dependent on the amount of cosmic ray that it hit the boulder, it's important to make sure that the boulder is not shielded by the topography around us. In this particular case, as you can probably see, there's very little topography higher than us, so the shielding is minimum. Okay, this is our last day of fieldwork. We just crossed the river. This is a massive glacial deposit, probably the last advance in this new valley that we're exploring today, not far from San Matteo. Okay, we're now back to Lima, ready to fly to Aberdeen tonight. We collected some 60 samples, which is very exciting. They will now be sent to Australia, and where they will be processed to find out what age those samples have, how long ago those now disappeared glaciers deposited those moraines, those glacial deposits. It's a bit strange to be back to a big city with a lot of tourists, also commodities, and yeah, it's a bit of a different Peru than the one we experience up in the mountains. but it's time to go back indeed.